Hello. We've got chat box there. Okay, how many do we have? We have 6 students. I'll wait a little more.
Dr. Small, I have a question. Would you be able to explain part D of the homework at any point today?
Yeah, remind me what part D was asking.
To graph the new equation that we get for the new image.
Yeah, so you take each term and you had what 1.25 plus something times cosine of 2 pi x plus, I think it was just cosine 2 pi x plus some plus 1/4 of cosine 4 pi x. Is that right?
Yes.
So the 1 gets multiplied by 1 and the cosine 2 pi x gets multiplied by whatever number that you would get when you plug 2 pi into that point, into that MTF. And the 1/4 cosine 4 pi x would get multiplied by whatever you get when you plug 4 pi in.
Oh, okay, that was my mistake. I guess I didn't think it was that simple then. I was trying to do something else completely different.
I could make a much harder problem if you would prefer.
No. This is perfectly fine.
Okay.
I just have to pay a little bit more attention. That's all.
Okay. How many do we have now? Wait 2 more minutes. Time is it? 1 more minute. So any questions about fall classes while we wait, since I've been doing a bunch of work on that behind the scenes?
This isn't about classes, but I had a question pop up in my head. So,
Okay.
how do like when you're if you have a camera, right, that has like an auto focusing system,
Mhm.
and let's say you have you're taking a picture of someone or like whatever object, and then you of course have the background. How does the camera distinguish like what part should be in focus, or like how to, you know what I mean? Like if there's two different objects that are in an image that are at different lengths.
Yeah, so one of them is in the foreground and one of them is in the background.
Yeah.
And they're at different distances, so you can either focus on one or the other. Okay, I've never worked on those algorithms, but my understanding is that first and foremost, people generally tend to center the field, center what they're interested in. There are exceptions. There are times when you want an artistic effect from having someone off center, but in the most common case, if you want to center someone, and also often there's a way to indicate, you know, especially in newer cell phone cameras, there's a way to indicate what it should focus on. So that would be one thing. It's going to look for either the center or whatever you designate. How does it know that that thing is in focus? Well, it's going to look at the modulation transfer function, and I think it's time to get started. So that's actually a perfect question for starting today. I
Okay.
wish it's, I swear that was not a plant. That was not intentional. He came up with that without my prodding. But before we do that, we're going to say a little bit more about Gaussian beams and Gaussian point spread functions, just to wrap that up. Remember, we had been saying for a few classes now that you can approximate a the diffraction limited pattern of focused light with a Gaussian. So you have a bunch of rays, and ideally they would come to a focus like that, and everything would pass right through there. But we know that that's not what really happens. What really happens is that the light, for a while, behaves pretty much the way ray optics would predict. It's going in a fairly straight line, but then as it gets close to there, it veers off. It cannot come to a perfect focus because, of course, light is a wave, and we cannot focus a wave to a spot of zero size. And so it has some beam width, I'll indicate it in blue, some width, and it's a function of z, the distance from the focal point. So it should be W of z. And we said that this beam profile is roughly hyperbolic. It looks roughly like a hyperbola. So W squared over W naught squared minus Z squared over Z naught squared is 1. And W naught is the minimum width, which we will say is about 0.6 lambda over n sine theta. Now, some people might define it a little bit differently. It would all depend on exactly what you're going to define as the edge of the beam. Are you going to say where the intensity is decayed to 1 over E times its maximum value? If I naught is the max, here's I naught over E, here's I naught over E squared. People come up with different measures like that. And then we said that, well, if, okay, we could solve for this. So W is equal to W naught square root of 1 plus Z squared over Z naught squared. And we noted a few things. For starters, we noted that if you're very far from focus, then, well, these rays, the light is almost behaving like a ray. It's almost obeying the equations of geometrical optics. So in that case, W is roughly, Z is much larger than Z naught. And W should be Z tan theta, because this is the angle of divergence, how much the beam is how far it is from the axis. So here's W, here's Z. W is Z tan theta. And of course, if Z squared over Z naught squared is huge, we can ignore this one. And so we're left with W naught Z over Z naught equals Z tan theta. And from that, we conclude that Z naught is equal to W naught over tan theta. Now, let's try to interpret this. First, we could ask, well, what on earth does Z naught even mean? And one way to figure out what Z naught means is to just plug in Z equals Z naught. If Z equals Z naught, well, let's see here. So we got Z naught squared over Z naught squared, that's 1. W is W naught square root of 2. So Z naught is just a measure of how far away from focus you can go before the beam width has increased by about 40%, because square root of 2 is 1.414. So multiply by 1.414, it's increased by 40% if you go Z naught away. That would be one way of interpreting it. Now, another thing we could note is that if, let's see here, Z naught is 0.6 lambda over n sine theta tan theta. So if we have a paraxial beam, Z naught is huge. This blows up for small theta, right? If you have a paraxial beam, then you can go quite a long distance from focus before the beam has spread out all that much. Any questions on this? All right, so in general, we're going to say that I of Z is equal to is equal to some constant. I'm just going to call it A for now. A e to the minus R squared over 2W squared. Right? And you'll see why I do that. W squared, of course, depends on Z. And now let's try to work out what the profile of the beam would be. What is this constant A? Well, let's see here. We usually, if we talk about, say, a laser, we'll say that we'll usually talk about the output of the laser as a power. We'll say it's putting out however many milliwatts, all right? But intensity isn't power. Intensity is power per area. So how could we use information? How could we relate information about the power in this beam? How could we relate that to the formula for the intensity? Intensity is power per area. But here, it's not like we have a uniform intensity. So you've got some finite power spread out completely uniformly over some finite area. This diagram up here is an oversimplification. If we were to actually make a plot of beam intensity versus distance from, versus distance from the center of the beam, it's not like over here. It's not like this, okay? It's not like here's R, distance from the center of the beam, and here's W. And over here, it's one number, and out here, it's 0. It's not like it goes from something non-zero to zero. What we've really got is something that spreads out like that. I meant to take a color that stands out a little bit more. What we've really got is something like that. And we define the edge to be where the intensity is sometimes 1 over E, sometimes 1 over E squared. You know what? I think I'm going to make this a 2 up here so that we're dealing with a 1 over E squared distance, because if R equals W, then I of RZ, I know I just wrote a Z, but I should have written it as a function of R and Z, equals e to the minus 2 times some constant A. So how are we going to relate the power carried by this beam to some formula for the intensity? Someone tell me. Anyone? Anyone? Bueller?
Professor, so we have intensity and you're asking us to how to relate that into power.
Yes.
Don't we just get intensity times the area?
Well, we could write that if the intensity was a constant and the area was just one number. If we just had one intensity in one area, we could do that. But we're going to have to take the surface that this light is traveling through. All right, we've got our axis, we've got rays of light traveling through some surface. Okay, and we're going to have to take whatever surface the light is traveling through, and we're going to have to deal with the fact that over here it's very intense. Now out here it's less intense, and out here it's less intense still. So what do we do when it's not just multiplying one number by another, but we have to look at the entire area and take into account that in this part of the area, the intensity has one value, and then that part has another, and then that part has another.
You have to integrate over the entire area.
Thank you. Thank you. So P equals integral of I dA, or we will integrate from, I'll put this constant, I should not have called that constant A, because I'll call this I naught, and I naught, because A is area. So that's I naught integral. I'm going to integrate in polar coordinates because we have a, if we look at a cross-sectional area of the beam, it's circular. So theta equals, phi equals 0 to 2 pi. Theta is the divergence angle. I don't want to double up symbols any more than I have to. R equals 0 to infinity. E to the minus 2r squared, r dr d phi. And what I'm going to be left with is, well, let's see. And that should be an r squared over w squared. I don't see a phi anywhere in that integrand. So the integral over phi is just 2 pi. 2 pi I naught integral from 0 to infinity r e to the minus 2r squared over w squared dr. All right, let's see. I'm going to make a u substitution. I'm going to say that u is r over w. So r equals w u. dr is w du. And then I get 2 pi I naught integral from 0 to infinity. Let's see, r is wu, dr is w du. So I get a w squared e to the minus 2u squared du. Oh, there should be a u du. All right. We're going to get a 1/4 when we do the integral because it's 2 pi I naught w squared negative 1/4 e to the minus 2 u squared. Any questions on where that negative 1/4 comes from? If you just take the derivative of this exponential, well, the derivative of an exponential is itself, but then you take the derivative of the exponent, and d by du of minus 2u squared is minus 4u. And we know that there should be a factor of u there. We need the minus 1/4 to cancel out the minus 4. And so when all the dust is settled, we are left with pi over 2 I naught w squared equals the power. I naught is equal to 2 times the power over pi w squared. So the maximum intensity is equal to 2 times power over width squared times pi. So if we just treat it as a circle, all right, which is an approximation, if we treat it as a circle, we get that the maximum intensity is basically twice the power over the area, which, and you might say, well, why isn't the intensity the power over the area? Well, you would expect the average to be the power over the area, and then you would expect the maximum to be equal to be somewhat greater than the average. And here it's just 2 times the power over the area of a circle. Somebody must have a question. If we plug everything in and we remember that the width is variable, the width depends on how far we are from the focus, then what we finally get is that the intensity as a power of distance from the axis and distance from focus is 2p over pi w naught squared 1 plus z squared over z naught squared e to the minus 2r squared over w naught squared 1 plus z squared over z naught, z naught squared. This is, of course, an approximation. Everything with Gaussian beams, almost everything with Gaussian beams is an approximation. There are ways to make truly Gaussian beams. In most cases, Gaussian is, in many cases, Gaussian is an approximation. If you really need to work with Gaussian beams, these approximate formulas that I'm giving you here are just the beginning. There's a whole more elaborate terminology. Most advanced optics books will have a section on Gaussian beam profiles. I would say that the book by Saleh and Teich is a perfectly fine place to start. Again, it's not the most mathematically rigorous, but it covers things at a very practical level. Saleh and Teich, Fundamentals of Photonics. And then there's the Lasers book by Siegman. which is more rigorous. There's, it's called quantum electronics by Yarev. All of these are good places to go for more detailed treatments. But if you just keep these basic ideas in mind, they'll take you a long way as you're puzzling out all of the notation in there. Remember, this is a first optics class. The things to remember are that beams focus, but they don't focus perfectly because light is a wave. Far away from focus, we can use geometrical optics with reasonable accuracy. Near focus, we absolutely need to pay attention to the wave nature of light. And because the profile, the intensity profile, doesn't cut off perfectly, but in fact, decays gradually. If you need to approximate with a Gaussian, you're going to have a width that increases as you go away from focus. And a formula like this is a very good starting approximation. You can refine it as needed. Somebody must have a question. Well, if you need to refine it, these are the books that I usually turn to when I need to refine my understanding of Gaussian beams. I kind of like this one because it has a little bit of everything at a very practical, sometimes qualitative level. I like this one because it has a little bit of everything at a pretty in-depth level. This one is incredibly in-depth, and actually for some aspects of a laser, for understanding the mechanism and meaning of spontaneous and amplified emission, it's absolutely superb, but it's also not necessarily as encyclopedic. It's very in-depth on what it does, though. No questions?
This isn't really a question, but more like an observation.
Yeah.
That if you take z to the limit of a large number, then it goes. We see that the inverse squared law for the intensity pops up.
Ah, yes, very good point. If z is very large, then the denominator of the exponent blows up. When the denominator blows up, the exponent goes to 0. And we're left with 1 over z squared. Yes, that's a very good observation. So basically, we could treat it as a point source emitting over some finite range of angles. I like that. I like that a lot. And indeed, that's perfectly consistent with what we know. I mean, if you shine a laser pointer on something very far away, it does look pretty uniform. Okay, fine. So we've been talking about how the point spread function behaves like a Gaussian. And if you go away from focus, it spreads out. Now let's get a little more into what the point spread function really is and how it's used. I'm not going to test you on all of this. I'm going to give you a mix of a very practical point of view and the beginnings of the in-depth theory. If you only need the practical point of view, great. If you have to study the in-depth theory, I like the Fourier optics book by, oh my God, I just blanked on the author's name. And I studied, and I have that book right here. Fourier optics book, Fourier Optics by Goodman, for a lot of that theory. Again, I'm trying to give you the first step so that when you go in there, and all of these books tend to go very rapidly into notation, you're not completely lost on what is the point of the notation. that that the basic physical idea is there. All right, so we know that a lens blurs out an image because it cannot focus a point object to a perfect point image. So if I have a point object here, then the image that it would form on a screen or a detector would not be a nice perfect point like that, but rather would be blurred out like that. And a real object has many points on it, and I'm going to draw them in different colors just to distinguish them. So each point, rather than being perfectly focused like that, would instead get blurred out like that. And if they're far enough away, great. But if we had something in between them forming an image, well, then everything's going to overlap and it's a blur. So if we have many point objects, I could say for each of these, if these point objects were at a height y, then down here they will be at a height minus our magnification times y. And our image would be the sum over the objects, which I'll denote with the subscript I, the intensity, the maximum intensity that each one would produce, times a PSF of y minus yi, where yi is going to be minus the mag times y object. All right, so whatever height it was at, multiply it by the magnification. That's the idea. We're just adding up many point spread functions on the detector plane. Any questions so far? I'm doing this in one dimension. Of course, it should really be done in 2 dimensions, but you don't lose a whole lot by doing the theory in 1 dimension. Almost everything, pretty much everything that I can think of, unless you get to certain things with normalization, making sure that the integral of certain things adds up correctly, then you have to pay a little more attention to issues of polar coordinates versus spherical, and what are the units, what are the units of this I in front. Then 1D versus 2D have some differences, but essentially all of the key ideas can be communicated with just a 1D model. Well, as long as we have discrete points, we're fine. And often we do have discrete points. I've said many times that in biology, you fluorescently label a cell. So like, let's say that inside the cell, we've got the nucleus, it's got the little double helix, the DNA coils, and then there are many other parts in there. There's the cytoskeleton, there are various surfaces on which key reactions are carried out. Of course, the membrane is really a double phospholipid bilayer. Double bilayer is redundant, you know what I mean? So there are many things inside the cell we would want to look at. And cell biologists will say, okay, maybe today all I want to look at is these filaments of the cytoskeleton. I make some molecules that do 2 things. 1, they glow when you shine the right kind of laser on them. 2, they attach to the filaments of the cytoskeleton. Great. Well, there you're looking at a bunch of point objects. So summations of point objects are important in a lot of optics. They're important in a lot of the optics that I spend the most time studying. But a general object, you would have an infinite number of points infinitesimally close to each other. And when you have an infinite number of things infinitesimally close together and you have to add up all of their contributions, what kind of mathematical procedure do you think we're going to follow?
Integral.
Integral, yep. So then what we would say is that our image at a point y on the detector screen is an integral over the object. There's going to be a density. So you're going to have at a point y prime in the object plane, you say, okay, what is the density of things sending light into that lens? Whether those things are glowing of their own accord or reflecting light is not really important right now. What matters is how much stuff do we have sending light to us? What is the density of light emitters? For our purpose, they're emitters, even though maybe they're really reflectors. All right, what is the density of stuff? And then we're going to put y minus y prime. You might be saying, shouldn't we include a factor of magnification? Ideally, yes, but let's pretend that this is one-to-one imaging. If you want, we can just say that what we're really adding up is some equivalent position. Okay, so we're asking what is the position in the image plane that would correspond to this position in the object plane. I just want to, what I mean is, all I'm saying is, okay, I got to figure out how many objects do I have at some coordinate y prime. All right, which would be here in the object plane, but how many objects do I have that would produce an image centered at this point? Okay, that's what I want to know. How many objects do I have that would produce something, an image centered there? That's rho of y prime. Then we multiply by a PSF, a distance y minus y prime away, because I'm not necessarily measuring the light right here. If we formed point images, if we formed perfect point images, well, then all of this would be easy and we wouldn't really have to even develop any theory. It would just be, it would be a trivial thing that no one will ever pay you to do because it's too easy. Anyone could do it. But in fact, an object that would produce an image centered here also sends light to here and here and here and here and there and there and there. And so if I want to figure out how much light I get right here at a point y, I have to say, okay, well, I'm going to have some image centered here, but it's producing a tail that comes out to y. So I've got an image centered at y prime. It's got a tail that goes out to a point y where I'm actually detecting. How bright is that tail? How much light is making it into the tail? That depends on y minus y prime. If y is really close to y prime, so like I was actually right here, well, a lot of light. The PSF, point spread function, is pretty big. If I'm way down here in the tail, my point spread function is pretty small. Then I add up over all of the y prime values, because after asking how many things could produce an image centered right here, then I ask how many things could produce an image centered right here. And now I've got a different y minus y prime. So I have to say, okay, well, this point y where I'm detecting, how strong is the PSF tail when I'm a distance away given by this y minus this y prime? I add that in. Then I say, okay, now how many things are producing an image centered right here? And that's this row. Well, How much light will they send to a point over here at Y? Again, PSF evaluated with this Y minus this Y prime. Any questions? This concept shows up for more than just imaging. I'm doing all of it in the context of imaging, but what if we had some instrument? What if we had a spectrometer? It doesn't even have to be an optical spectrometer, which we'll talk about in a few weeks. What if we had an electron spectrometer or a muon spectrometer or whatever? We had something that takes particles of whatever type, whether maybe it's designed to look at photons, maybe it's designed to look at electrons, maybe it's designed to look at neutrons, whatever. We've got something that takes particles in and tells you how many particles it received at each energy. And it says, all right, we got this many particles at 10 keV, we got that many particles at 20 kilo electron volts, and that many at 30 kilo electron volts. Well, in principle, if I send in a bunch of particles with energy 10 keV, I should get a spike right there. I should just get a nice big spike. But in fact, my detector isn't perfect. If I sent in some particles with energy 10.01 keV, whatever piece of the instrument is detecting 10 keV would probably still pick something up. And likewise, if I sent in something at 10 keV, whatever's picking up energy at 10.01 keV would probably pick something up. So I don't get this nice spike. Instead, what I probably get is something that looks like this, just because the instrument can't tell you perfectly, oh, that was definitely 10 and not 10.01. It has nothing to do with the quantum uncertainty principle, or at least it doesn't have to have anything to do with the quantum uncertainty principle. Even if we sent in particles whose energy was well enough to find that the energy uncertainty was really minuscule, the detector will never be perfect. And so if I wanted to know how much signal I get at a given energy E, I would have to integrate over all the possible input energies. And I'd have to ask, how many things were sending in energy, particles with, how many particles with an energy E prime were coming in? And then we'd have some response function of E minus E prime. Because if I get something that is really a 10.01 keV, the little part of the instrument that responds to 10 keV will probably still go off. It'll probably sound a little buzzer saying, hey, I got something. As will the part of the instrument that responds at 10.001 keV and 10.002 and 003 and 004 and 00 whatever, 009 and 01. You see? And so everything will spread out. Unless we built an instrument with really clunky resolution, then maybe only one detector will go off at a time. But if we make it and if your thing has really clunky resolution, you could say, no, it's really good resolution. Only one thing goes off. And I say, well, if you can't tell how much it's spread out, it's not actually that good. Any questions so far? What I want you to take away is that these kinds of integrals where you've got something about your input, whether it's how many objects are emitting light that would produce an image centered at Y prime, or how many objects are coming in with an energy, multiplied by something that depends on how your instrument operates, and the difference Y minus Y prime, those show up a lot in scientific data analysis. Now, I don't know, did the idiot who taught math methods last semester, did that idiot tell you anything about convolution integrals?
Oh yeah, I was gonna say that looks a lot like a convolution integral.
Yeah. Yeah, I heard that the jerk who taught math methods last semester talked about a convolution integral. And one nice thing about convolution integrals is that as messy as they look, their Fourier transform is really simple. Okay, now for those who didn't take math methods yet, a Fourier transform, and I'm not going to test you on any of this. A Fourier transform is a way of taking a function or a signal and breaking it up into sine waves. And we break things up into sine waves for the reason I gave a few weeks ago when we started wave optics, partly because sine waves are kind of like sine waves are to functions what the periodic table of elements is to chemistry. They contain, you can make almost any function out of them. You can make basically all the functions we care about in physics out of them. Mathematicians could construct functions that you could never make out of sine waves. We rarely care about those. But all of the nice, smooth, continuous, differentiable, well-behaved functions that we care about in physics can be broken down into sine waves. And solving equations with sine waves is easy. Just like analyzing things in terms of chemical elements is, at least in principle, easy. Not to put down chemistry or say that chemistry is easy and have a bunch of angry chemists come and say, no, our subject is hard. The point is that you get insight by thinking of matter as made out of elements, and you get insight by thinking of mathematical functions as made out of sine waves that obey simple equations. All right, so we could take an image and we could break it down into sine waves. And if we broke it down into sine waves, so if we wrote this as, people sometimes write I tilde of k, that's the Fourier transform of the intensity. That just means that the intensity is an integral or an infinite sum of a whole bunch of different sine waves, each of them of the form e to the I kx multiplied by the intensity of that particular sine wave. So if I want to find the intensity at a point x, I can get it by I can write it in terms of a bunch of sine waves. And likewise, I could say, well, okay, well, that was, so the intensity, the actual image we get is just a bunch of sine waves. Now the object, I should have written this as y, to be consistent. The object, likewise, could be written in the same way as, this is one of the common notations. They just put a little tilde over it to mean that this is the Fourier transform of the function rho. And we're summing over k values. And then, of course, PSF, distance y from the origin, or from wherever you're measuring, would be the same thing. Any questions? So any function we care about in physics can be broken up into sine waves, and we can write the Fourier transform of all three of these things, the image, the density of sources that produce the image, and the point spread function of the instrument that produced the image. And so we can say that I tilde of k is equal to rho tilde of k times PSF tilde of k, because the intensity was a convolution, and it's a fact derived in math methods that if you've got a convolution integral, if something is equal to a convolution integral, the Fourier transform of that something is the product of the Fourier transforms of the things that you convolved. Now, what does that mean? Well, this thing is called the modulation transfer function, okay? Because what it's saying is, if I have rho of k, if rho is some sine wave modulated at spatial frequency k, and you may be thinking, wait, spatial frequency, we're used to thinking of frequency as the number of cycles per second. Well, sure, that's the most common definition of frequency, the number of cycles per second. But once you get down to periodic functions, a periodic function is something that repeats. It might repeat in space, you know, like the lines on a ruler repeat, the lines on this graph paper grid repeat. It could be something that repeats as a function of some other variable. If I had, I don't know, a function of energy, and whenever the energy was either 1 EV or 2 EV or 3 EV or 4 EV, something happened, you could have a periodic function of energy. You have a periodic function of anything, all right? A function that repeats whenever a variable increases by a certain amount has a periodicity, it has a frequency. That's just how many times it repeats per unit of its input variable. So a function has a wave in space has a spatial frequency. All right, it repeats every lambda. So it has 1 cycle per lambda, or 2 pi radians per lambda. So k is 2 pi over lambda. So if I have some sine wave modulated at a spatial frequency k, the image of that sine wave is rho tilde of k times PSF tilde of k. This is the object wave amplitude. All right, we'll say that this is rho tilde of k. This is the height of your object. And then we take this is our input object, send it through a lens, send it through some imaging device. What finally gets output on the screen is this, something with something that's a little less stark. So, you know, if I was trying to draw this as something that goes from 0 to 1. But what I get instead is something that goes from 0, well, scales from 0 to 1. So maybe it goes from 0.4 to 0.6. Okay, we have something with a reduced amplitude. I tilde of k is the image reduced amplitude. We would love it if the amplitude were the same. And for low spatial frequencies, it often is. But if it gets blurred out, then the amplitude is reduced. Any questions? We're giving you a lot of new concepts to chew on. Surely there's a question.
Well, I just had one question about the up above a little bit with the Fourier transform equations a little bit further. So on the right there for down at the bottom now, the PSF, is that on Y or K? The input?
Oh, that should have been K, my bad.
Okay, yeah. That was just confusing me.
Other questions? So I'm going to switch to my other device. I'm going to go into a program called ImageJ, which is a free image processing software, free image processing program used by a lot of biologists because it was produced by NIH. And we're going to process this with an FFT filter, with a bandpass filter. So what we're going to do is we are going to run this through something that takes out, first we'll take an image of the Bobs from Office Space, and we'll run it through a filter that takes out the high spatial frequencies. Actually, no, we're going to leave the large structures in. So I'm telling it to only take out structures bigger than 1,000 pixels, but there are no 1,000 pixel structures. I'm going to tell it to take out anything down to like up to like 5 pixels. All right. What I've done is I've just, if we imagine that this picture of the Bobs was a sum of a whole bunch of different sine waves, I told it to take out any sine waves whose period is smaller, whose wavelength is smaller than 5 pixels. So I take out all of the sine waves with the really small wavelengths. And what you should notice is that the Bobs got slightly fuzzier. I can undo that and they look sharp. But then if I redo that, and I'll take out a, oh wait, that was the Fourier transform of it. It doesn't look like much. If I do a bandpass filter, instead of taking out anything up to 5 pixels, let's take out 10 pixels. Now the Bobs definitely look blurry. I've taken out the high spatial frequencies, which means the sine waves with the small wavelengths. If I take out the small wavelengths, I'm taking out the small structures, and the Bobs look fuzzy. The Bobs look to us the way they would look to themselves if they took their glasses off. Any questions? Can someone tell me what it is that the bandpass filter, it does here? What do you do here is the question that Bobs would ask in office space. Does anybody have a question about what it is that these bandpass filters actually do here?
I'm a bit confused, to be entirely honest, just because like what an image actually is just a bunch of pixels, and then all those pixels have like an assigned RGB value. So like,
Yeah, they do have an assigned RGB value, okay? And so we could think of that as a function of X and Y, something that's saying the RGB value at X equals 1 is this, and the RGB value at X equals 1, Y equals whatever. At this value of X, Y, and Z, here's the RGB value. And another value of X, Y, and, well, not X, Y, and Z. At this value of X and Y, here's the RGB value. At another value of X and Y, here's the different RGB value. So you could think of the image as a function of X and Y, right? Something where you give it X and Y, and it tells you, okay, here's what the RGB values are. Then I could take that function of X and Y and Fourier transform it. And now I've got a bunch of sine waves. And so I could think of those RGB values as a combination of many different sine waves. Those X and Y values the value at a given X and Y is the sum of a bunch of sine waves. Now, if all I want to do is tell you the image, I probably won't do that. But the reason why I would filter it, it's not so much that anybody would look at this and say, oh yeah, I definitely want to make the image less sharp. Because frankly, in this—
Are you showing an image? We just see your desktop screen.
Do you see this image of the Bobs moving?
Oh, with your cursor on it?
Yeah.
I was looking at the wrong thing.
Okay.
I didn't realize that was it.
Yeah. So let's undo. Okay, again, here's the Bobs. It's a nice sharp image. Frankly, the sharper, the better. You see all the imperfections, and that's what you want in this movie. And then we do a bandpass filter. So we get rid of features. We get rid of, say, the short wavelengths. And that's what you get. Now, sometimes people actually want to get rid of the short wavelengths. It's been observed that sometimes if you take old color TV shows and color movies and you show them in HD, well, not too old, but if you take movies and TV shows from the 90s and early 2000s, and then you show them in higher resolution, they actually look bad. You see every flaw on the human being's skin. And sometimes they don't want that. So sometimes people actually would want to process out the high frequencies. Other times we process out the high frequencies just to show what it does, because as I'm going to demonstrate to you, all imaging devices remove sufficiently high frequencies. That's what blurring is. And so this is a more dramatic illustration of how the blurring works. Other questions? I'm going to restore the Bobs, and then I'm going to do a different bandpass filter. So I'm not going to take out any of the high frequency stuff. We're going to leave in all of the high frequency stuff. I'm going to take out the low frequency. I'm going to take out the low frequency down to, oh, I don't know, 100 pixels. It's not obvious, but when I take out the low frequency, the low frequency, which means large structures, because now we're talking large wavelengths. Do you see how a little bit of the color changed on Mr. Slidell's suit there? Let's take out still pretty long wavelengths, but let's go down to 50 pixels. See how a lot of colors are starting to get weird? We're definitely seeing weird things, but what we're not losing is the sharp details. Okay, now we've lost a lot of things in the colors. So it's harder to really explain what's going on when you take out the long wavelengths. But taking out the short wavelengths, it's very clear what's going on, or it's by definition unclear because you lose all the sharp details. Whereas when you take out the long wavelengths, it looks kind of funky because you've got all the sharp details, but nonetheless, the things like the shirts, which are a more uniform color versus the face with a lot of details, the shirts change, the cubicle dividers change, the ceiling has changed. Any questions? So if you take nothing else away, take away that spatial frequencies are basically things that hold information. All right. And the spatial frequency, the different spatial frequencies in an image are, it looks like it can only undo one step at a time. Doesn't matter. I can always reload it if I want. No questions at all on what the high frequency, what it means to remove the high frequency stuff?
I was kind of relating it back to that RGB question. So, like, say you are removing the high frequency stuff, but before in Bob's image, you split the channels to your red, green, and blue.
Mhm.
So if you're moving high frequency, would the blue image look vastly different from the red image?
Well, that depends. Do I want to save the changes? Absolutely not. All right, that's my screensaver from, or those are two characters from Orphan Black. So let's see, where are the Bobs? Okay, so here are the Bobs again. It's not my screensaver, it's my desktop image, which right now is from Orphan Black. All right, so can I split it? Yeah, split channels. Okay, now you're thinking, wait, this doesn't look blue or red or green. It looks black and white. Well, this is just a scale of 0 black to 255 white. This is the intensity of the blue part. This is the intensity of the red part. And this is the intensity of the green part. Now, can I recombine them? Stack to RGB. I'd have to load them as a stack. But suffice it to say that if I had a bunch of, if all of the details were in red objects, then doing, or if there was a portion of the image where a lot of the details were red, then doing a high pass filter or a low pass filter, taking out the high frequencies would only remove red details. It wouldn't really change much of the blue or green. Does that help?
Yeah, that answers my question. Thank you.
Like you'll notice here that there's actually more in the red channel on their faces than there is in the blue or green. And that's because, well, basically their skin is kind of pinkish. And so because their skin is pinkish, it is going to be disproportionately in the red channel. And let's see, you can tell that their ties are at least somewhat reddish because particularly this one, there's a lot of detail in the tie in the red channel. and not as much detail on the tie in the blue and green channels. Other questions? Okay, I'll just talk for a few more minutes and then we'll take a break. All right, so the idea of a modulation transfer function, again, is we ask how much, if we want to understand what we're if we want to understand the spatial frequencies in our image, we have to look at, well, what was the object and what was the lens that produces the image ultimately going to pass? It really goes back, let's again think about the point spread function. All right, the point spread function, instead of just having a couple of lines like this, we instead get things that are spread out. And because they're spread out, what we wind up getting is, if I were to add these, we'll do it in a different color, not because of RGB channels, but just to distinguish things. It's going to go to about there, about there. It's going to look more like that. All right. So because of that overlap, the overlap we get a blur. So instead of having things rise and fall sharply, instead of having sharp rise and fall, we get much more gentle rise and fall. That's the whole idea of blurring. You lose sharpness, whether you think about it as some point objects getting spread out so that they start to overlap instead of having, you know, a true spike here, here, and here. Everything spreads out and overlaps. Or you think of it as a wave that goes from being like, let's see if I could do it like that to like that. A wave that becomes less sharp. And if we go back to this equation, that the intensity, the image at a spatial frequency k is equal to the object times the PSF. That's just equal to the ratio of the image or the output to the input. It's got to be less than or equal to 1. So if the point spread function is less than or equal to 1, if the point spread function is less than 1, you're losing a little bit of sharpness. Now, if I redid this image, if I redid this example with everything spread further apart, nice spike there, there, and there. So now everything is spread farther apart. And I still just do like that. Now, strictly speaking, here there's a little bit of light getting in there. So if I add up those lights, okay, doesn't quite go to 0. You know, instead of getting something tiny, I get twice something tiny. So it's a little bit further from 0. But still, this is really minuscule. We're hardly losing anything there. So I would say that our modulation transfer function is close to 1. It's approximately 1. All right. This is, somebody might say, how do I strictly measure a modulation transfer function from that? I'm saying it's analogous to a situation like that. So if I'm looking at something like this, very large spacing, spacing is much larger than the spot size. Our modulation transfer function is very close to 1, whereas here, the spacing is comparable to the spot size. The MTF is definitely less than 1. So modulation transfer function is just another way of quantifying resolution. We've been talking a lot for most of the semester. We would talk about spot size. We'd say ideally a point image will form a point object will form a point image. In reality, it forms a spot. Let's see how big the spot is. And that would give you an idea of the resolution, because some detail that's supposed to be smaller than the spot size is just never going to show up. Well, instead of talking about spot size, some people will talk about the inverse of the spot size. So they'll talk about the number of lines per millimeter. They'll either talk about lines per millimeter or 2 pi over the size, i.e. radians per millimeter. Oops. Tiny spot, large K. Large spot, small k. So when people want to talk about tiny spots or sharp features, they talk about large k, large spatial frequencies. If they want to talk about large features, they talk about small spatial frequencies. Any questions? Let's take a 10-minute break. Okay, I'm back. Had 10 minutes to think and chew on things. Anybody have a question now? So again, the basic idea of modulation transfer function is if your input was some oscillation with whatever amplitude, your output, your image, will be an oscillation with a different amplitude, probably a smaller amplitude. How much smaller? If it's essentially the same amplitude, that would be like the case of objects that are much farther apart than the size of your point spread function. So, okay, you've got pretty much perfect fidelity there. If, on the other hand, it's a substantially smaller amplitude, that's like having objects who are about, whose spacing is comparable to the spot size or the size of the point spread function. Now, people talk about modulation transfer functions for a lot of reasons. To be honest, sometimes it's because a lot of math is easier. Sometimes it's because Fourier, a lot of things actually are easier working with Fourier transforms. Sometimes it's because it's more convenient to think about how many objects do I have in 1 millimeter or 1 centimeter or whatever, instead of what is the size of an object? How many things do I have to fit into a field of view? Here's another reason why modulation transfer function is sometimes better to work with. If I measure a point spread function, well, I would have to take a point object, take a picture, and see how much it gets blurred out. Now, that was in the center of the field of view. If there's one thing we have learned from working with Zmax, it's that off-center objects in real lenses are rarely as good. So maybe over here, you've got terrible, terrible coma aberration. And maybe over here, we've got a combination of coma and astigmatism. And so it's highly elliptical, whereas here it's more teardrop shape. There's lots of things that could happen. All right. I'd have to image a point centered here, and then a point centered there, and everywhere else. How do you think I'd measure a modulation transfer function? One thing I could do is I could take a picture of a ruler at different magnifications. All right. The ruler, the marks are evenly spaced. Take that picture at different magnifications. And boom, I've covered this entire center line. You know, maybe they're taller, but the point is that you can take pictures of a ruler or something. All right, so there's a very natural way to measure a modulation transfer function to work across an entire field of view and just see, well, what I get out, does it look fuzzy or does it look sharp still? Right? That'd be a very natural way to do it. Take the picture of the ruler at different distances. How far away does the ruler have to get before it stops looking sharp and starts looking fuzzy? How much do I have to magnify or demagnify it before it changes from sharp to fuzzy, or vice versa? That would be one very convenient way of thinking about it. Another way of thinking about it is I don't know how to make a perfect point object. Okay, I know how to make, I know how to take a picture of a fluorescent molecule. That's usually close enough to a point. But you could always wonder about the finite point size. But a point spread function, a modulation transfer function is actually much more robust. What if this ruler isn't perfect? You know, I've got the features that are at, well, if this is lambda, I've got, when I take my image, I've got a frequency 2 pi over lambda. Now, any mistakes, you notice how I didn't draw these lines perfectly because I'm a bad artist? Well, if I'm a bad artist, all these little jagged, shaggy things, you tell me, those little jagged, shaggy things, are those going to contribute, modify the image at spatial frequencies much bigger than 2 pi over the mark spacing, or much smaller than 2 pi over the mark spacing, or at 2 pi over the mark spacing? Here's the spacing of the marks. Here's the size of those little jagged edges. The imperfections are tiny, right? And because the imperfections are tiny, that means that they're going to change the Fourier transform of the image. They will definitely change the Fourier transform of the image, but they're going to change it at high spatial frequencies. So I could take this it's pretty periodic, but still imperfect. Fairly periodic. Well, all those imperfections are at some spatial frequency much higher than what I'm trying to measure with the ruler. So I Fourier transform the image, and I just work with the spatial frequency that corresponds to the periodicity of the ruler, and all of my imperfections, my imperfections are going to limit all of my work. All of the imperfections on that ruler are going to be completely irrelevant. Questions? What do you think the spatial frequency of noise in an image is? Keeping in mind that any real image is pixelated. You know, we've got a bunch of RGB values on each and every pixel. That's how we represent an image. So we've got something here. If I've got something that's nice and red, it might take up several pixels. And then I'm just doing random things right now. I'm just adding in colored shapes for whatever, okay? All of these colored shapes that I'm filling in here are much bigger than a pixel. So this is, it's often called the window size. The window just meaning the range of things we're looking at. Noise comes from two things. It comes from the fact that the number of photons actually hitting a pixel is going to fluctuate from one frame to the next. And it comes from flaws in the electronics and random thermal processes in the electronics. So any fluctuation from one pixel to the next, pixel to pixel fluctuations, K is 2 pi over your pixel size. This is big. This is the highest spatial frequency you can see in your image. It's a fluctuation from one pixel to the next, okay? Actually, it would be a difference between two pixels. So it would have to be 2 pi over 2 times the pixel size. Because if something repeated every single pixel here, 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 then it would all look the same. So it would be a variation from one pixel to the next. So pi over a pixel. That's a really big number because the pixel size is the smallest length scale we have. So noise shows up at a frequency equal to pi over the smallest thing we can possibly see in this image. Your picture, your objects, everything shows up at 2 pi over your feature size, give or take. And of course, it won't just be 2 pi over that. It'll be stuff that's a little bit smaller than that, a little bit bigger than that, but it's gonna be around 2 pi over your feature size. And then if, say, there was some non-uniform shading, maybe this thing wasn't perfectly even and the lighting wasn't perfectly even, so it was a little bit darker here, a little bit brighter there. Well, that's a change that happens on a length scale of roughly half your window size. So about the largest size you could possibly see in here. So non-uniform background, that would be 2 pi over 1/2 the window size, or 4 pi over the window. Well, the window size is the largest size possible in this image. So your lowest spatial frequencies are background. Your highest are noise. What we care about is the object. So the Goldilocks frequencies, not too high so that they're noise, not too low so that they're background, but just right. Those are the image frequencies. And that is why people care about modulation transfer functions. Any questions so far?
Professor, there was a question when
In the
you were
chat?
talking. Yeah,
Okay.
it's during, I think, when you're talking about the jagged lines, I think.
Oh, could we use the bandpass filter to remove the imperfections from the ruler? Absolutely. That is one of the reasons for doing a low pass filter, to filter out the highest spatial frequencies corresponding to those minuscule imperfections. Other questions? So I want you to just practice using the modulation transfer function in Zmax. We've got about 10 minutes. I want to make one more point about what you should see on the assignment. And then I want you to just play with it. And I'll take questions on Zmax either the rest of today or on beginning of Thursday before. I want to tell you a little bit about what you should read for Thursday too. Okay, so I've been saying the modulation transfer function should be 1 for very low frequencies, corresponding to objects, to feature sizes much larger than the spot size. This should decay. And this is roughly 2 pi over the spot size. It decays to about a half at roughly 2 pi over the spot size. And again, that depends in part on how are we even defining the spot size in the first place. But it's going to be around there. Okay, you start to lose a lot of information when we get to 2 pi over to a frequency equal to 2 pi over the spot size. So now let's think, if we are in the diffraction limit, how does the spot size depend on aperture? You just did an assignment on this. It's proportional to the aperture width, the lens diameter is proportional to the square of it. Is it inversely proportional to the square of it or the cube of it or what? Try to remember.
The cube?
In the diffraction limited regime?
No.
It was inversely related.
It was inverse. It was 1 over the aperture. So this cutoff frequency, it's called the cutoff frequency because it's where it's decayed significantly. K cutoff is proportional to 2 pi over the spot, or 2 pi over 1 over the aperture. So that's got to be proportional to the aperture. Now, what about in the aberration limited regime? Now the spot size is proportional to the cube of the aperture. So the cutoff frequency is proportional to 1 over the aperture cubed. So what I want you to do on the project due next Tuesday is look at modulation transfer functions. And you're gonna set up a lens, you're gonna look at its modulation transfer function, you're gonna play with the aperture diameter. And when it's really narrow, you'll get one kind of modulation transfer function. If it's really wide, you'll get another one. You're just going to see what K cutoff is. You should find that initially it's proportional to the aperture, so it increases linearly. And later on, it should decrease as 1 over the aperture cubed. And there will be some transition regime. And this should be pretty close to where we found the minimum spot size on an earlier assignment. And so I'm basically asking you to verify that there's this inverse relationship between the cutoff frequency and the modulation transfer function and the spot size. Any questions? Okay, in the last few minutes, I want to tell you a little bit about Thursday's reading. Thursday, I want you to skim a paper and maybe look at a little bit of background documentation if needed. Basically, we're combining what was going to be the reading assignment for today with the reading assignment for Thursday. So go through the stuff that was put on Blackboard for today, skim all of it. We're going to talk about a very interesting paper on designing scan and tube lenses for microscopes. And the reason I want you to read this lens design paper is because I think of this paper as basically the most sophisticated lens design that a person could do without a degree in optical engineering. And appropriately, this paper was written by someone who has a bachelor's in physics and at the time was working on his PhD in biophysics and just wanted to improve his microscope. It's basically of the form, it's basically a project that along the lines of, we're not going to mess with the super expensive microscope objective. That lens would be designed by a team of engineers with PhDs in optical engineering, or at least master's degrees. We're not touching that. But we need to add one more lens on to the end of this to improve some scanning. What could we do? And so he basically goes, I think, about as far into lens design as a person could productively go without either an optical engineering degree or a decade of industry experience, learning lens design from senior engineers. If you spend enough time working at a job under the supervision of senior people, that's kind of like getting a master's in the subject. And so I want to talk about what he did as an example of the kind of practical problem you will often need to solve in a lab. Hey, I need to bolt one more lens or a couple more lenses onto the end of this instrument. How do I optimize it? What am I looking for? So skim the paper with that thought in mind. It's not so that you can understand every single detail of a Plössl eyepiece design or whatever, but first skim some of the background material that we were going to discuss today. We're just going to do a condensed version of it to try to understand what's a tube lens, what's a scan lens. And then, okay, what did he do? He tried several different tube lens and scan lens designs. And what did he find? As he added more lenses, how much did the different figures of merit improve? So at the beginning of the next class, first I'll give you a chance to ask questions about the ZMAX project, try a little bit of it between now and Thursday. Then we'll go over some details of how these kinds of microscopes work. And then we'll talk about what he did in that paper. Have a good day. Justin, you have a question?